Okay, guys. Also, one or two of you realize last Thursday I forgot to record. You ever see me not recording, please yell. I had the video here, but I just forgot to do it. Question? Lab reports usually return the week after, so in lab. No, I'll return the test. Okay, guys, let's get started. Test 2 material. Test 2 is two main topics: chemistry of alkenes, carbon-carbon double bonds, and then stereochemistry. Okay? Very important major topics. Everybody got a handout?
Last row.
Okay. Is there extra one somewhere? There's no extras anywhere? Maybe the copier didn't print all. I printed 115 and there's not 115 in here. I'm not sure, guys. We may not need the handout today. I apologize. I don't know what happened. Okay? We may not need the purple handout. What we need is the ones that I asked you to print out on your own. Intro to alkenes, thermodynamics. And reactions of alkenes. Everybody got 3 handouts that you printed out? Okay, guys, this handout here, Intro to Alkenes, which mainly is nomenclature. I did a video on this. As I told you by email, this will be video only. Nomenclature of alkenes. Here on the front side, on the back side, and it's largely on the back side of the first page is your easy terminology for the stereochemistry or the stereoisomers of alkenes when they're possible. Again, I have a video that covered the first page, front and back of that. The remainder of this handout we'll cover in class here. Please watch that video, and probably on Tuesday we'll finish up this handout and see if there's any questions about nomenclature. The other handout, one of the others is thermodynamics, kinetics teaser, top. We've got this one here. I think I'm going to cover this in class right now. We'll go through this fairly quickly. This is a lot of introductory, well, it's really review. A lot is review in terms of thermodynamics and kinetics, but we'll put it in the context of organic chemistry. The other handout is our reactions of alkenes. A little bit thick there, a lot to it. We'll be getting to that handout after the thermodynamic kinetic handout. Any questions? As I said by email, test 2 is going to be one of the more difficult tests you'll take with me of Organic 1 and Organic 2. Okay? 2 main reasons, but we're going to begin reactions. Now, acid-base chemistry is reaction, but it's very fundamental, basic mechanism. With alkenes, we'll have a number of reactions. We'll have mechanisms. We'll have complex, complicated mechanisms, involved mechanisms. If you do not stay on top of it and stay on it quick, ask questions, you're going to get behind and it will become overlooked. Okay? Typically, scores on test 2 drop about 10 to 15 points. All right? Try not to let it happen to you, okay?
Thank you for that.
Thermodynamics, kinetics. Okay, teaser. There's 2 reactions here. Decomposition reactions because the starting material, NF3, by the way I balance these, I'm not going to see me balance many reactions. NF3 will decompose and turn into nitrogen and fluorine. Also Ni3 will turn into nitrogen and iodine. Some bond strengths are given. Types of questions we'll see for this material. Which reaction above of the 2 gives off the most heat or energy? And if you want to use your calculator in organic chemistry, here's your chance. Otherwise, we're not going to use calculators too much in organic chemistry. All right. Which reaction above is endothermic? Which reaction will occur fastest? Which reactions, are the reactions driven by entropy or not? Now, if you can answer all those, we can end the lecture right now. Do we need to go over the material?
Yeah.
Well, most of that should be reviewed from Gen Chem. Okay? You did stuff like that in Gen Chem? What other information do you need? I hear there's more information needed. What information is needed? I give you some bond strengths here. What other information is needed? Big table of bond strengths. Bond strengths are also known as, basically it's the amount of energy required to break the bond. Sometimes called bond dissociation energy, BDE. We'll be using some of those numbers. You do not have to memorize all those numbers. The table will be supplied. Okay. I imagine we need to go over this, so let's go over this. That's what we need to be looking for. First off, some introduction. I'll say line reactions. What's a line reaction? A line reaction is where you show reactants, you show a line, and then you show products. Okay? That alkene reacts with HBr to give that alkyl halide over there. You could show a line reaction with a reagent on the line. Very often like the small reagent. Okay, this being the major organic reagent. You can do that. You can also show on the line conditions. Where here we have the reagent, we have 25 degrees Celsius and 1 hour. So these are examples of what I call, and most chemists call, line reactions. Okay, starting material, line. That line means yields. Those react to yield this. Okay. Thermodynamics. Well, you've seen plenty of thermodynamics in Gen Chem 1 and 2. The summary is delta G equals delta H minus T delta S, right there, right? Okay. You can read all that. I'm not going to waste your time. What is delta H? Enthalpy, which is basically heat energy. That's going to be your bond strengths. Okay. And this is already written on the next page. Before I turn to the next page, what is delta S? Entropy, randomness. Okay. And of course, which term does temperature magnify? Entropy, right? T delta S. Temperature magnifies entropy, right? It's nothing new though, right? Okay, delta H, I already said this. Energy change, heat energy. Delta meaning change. Change in the heat energy. Basically, this is going to directly relate to bond strengths. That's why I gave you a table of bond strengths. That's what we'll be using it. Okay? Calculate delta H. Which is favored? The positive delta H or negative? Negative delta H is favored. That's when products have lost heat energy. Negative delta H means that really means the system has lost heat energy. You can say the products have lost heat energy.
Would that be because they're going down to like a lower state of energy, so that energy is released?
Yeah, they're now at a lower state of energy because they have lost energy. That's going to be a favored reaction. What's favored in terms of entropy? Positive entropy, because what is entropy means randomness. Does nature want to become random or ordered? You call it ordered. Does nature want to become ordered or disordered? Disordered. Okay, if I drop a ceramic figurine here, it's going to shatter into many pieces. I don't think I'll ever see a figurine of many pieces come back together as one. Nature prefers randomness. Okay. My son's room on one day is clean and the next day it's not. It takes a lot of work to go the other way. So, which one's favored? Positive delta S. What's positive delta S? That means something has gained something. What does it gain? Disorder. Gain disorder. Okay? So because we're actually talking about disorder, you want to gain that. Again, this is nothing new, right? Okay. Delta H we'll calculate with a calculator. Delta S we're not going to calculate. We're going to assess it more qualitatively. And first let's do that. Delta S examples. Look at this first line reaction A. This alkene plus HBr gives this product. Let me make it so we can read it here. I shouldn't have even told you this, okay? The delta S is negative. Why? Because the system has lost disorder. Why? Why is that lost disorder?
One product, two reactants.
Because two reactants have come together and made one product. Two things coming together to make one. So it's became more ordered. That means it's lost disorder. That's a double negative, right? If it's lost disorder, delta S is negative. It's losing. Okay? You got to get the double negatives and all that right. Look at this reaction. What if this molecule converts to these two? That up there is an addition reaction. This down here is an elimination reaction. Okay? What if it eliminates and one molecule becomes two? There, delta S is positive. Why? Because the system, this is the system now, this side. It exists like this now. Has it gained or lost order?
Lost.
Well, see, I'm saying order. You got this double negative. Let's say order. Has it gained or lost order? Lost. It's lost order, so that means it's gained disorder. And if you gain disorder, delta S is positive. Is that favored?
Yes.
Yeah, delta S is positive. It's favored. What does favored mean? Favored just naturally. So we could say, basically, this here is the reverse of the top reaction, if you haven't noticed. Okay? Which one is favored by entropy? The second one. So if that was, that's really reversed. I could have drawn just a reverse arrow here and showed an equilibrium. And I could say which side is favored entropically. Let's look at this example down here. Here we have this molecule with an alkene, a ketone, and an alcohol making a ring. Now we have this ether down here. Spontaneously means isn't favored. Okay. I'll put a question mark here. Is delta S going to be positive or negative? One molecule going to one. Somebody tell me again. But why? Closing a ring. What is that? What is that doing to the water?
Holding it like tighter together.
Increasing order. Good. Good. Yeah, it is. Because if my hands are free, they can do all kinds of things. But if I put them together, I lose that flexibility. I lose the randomness. Making the ring, you lose the disorder. Is that right? You lose disorder, and so delta S is going to be negative. Yes. So is this reaction favored entropically? No. No, it's not. It's not favored entropically. Is this reaction favored by enthalpy though? We're going to have to do calculations. We're going to have to do calculations. Why does it depend on temperature? Why do you say temperature? Which term does temperature magnify?
Entropy.
Entropy. Would heating this reaction make it go to the right?
Maybe.
Which term does it temperature magnify?
Entropy.
Entropy, yeah. So do you want to magnify entropy to make this reaction go? No, you don't want to magnify the bad term. We said entropy is bad. It's not favored by entropy. Why would you want to heat it and make entropy even more bigger term in your delta G? Temperature magnifies entropy. No, you don't want to heat this. That make sense?
Yeah.
But really, this is review, right? Okay, so there's just some qualitative examples of entropy. Questions about entropy? Let's do enthalpy, heat energy. And here's an example. Very similar to the one above. I think I just got one less carbon here. One less carbon, and I drew in the H's. That alkene reacts with HBr to give this addition product. We're going to be doing this type of reaction. What's delta H for the reaction? How do we do this? We need to know what bonds were broken.
The double bond and the hydrogen.
The pi bond's broken. Everybody agree the pi bond's gone?
Yeah.
Okay, how much is the pi bond worth?
63.
Okay, now if you look at the table in the front, it says a lot bigger number than 63. That's because the table in the front, when they say pi bond, they mean the whole shebang, the pi and the sigma. Okay? But I got 63 from another table that's just for the pi bond. All right? Don't worry about where I got the number from, just look at these numbers, okay? So the pi bond's broken, it's worth 63 kcal per mole. What else is broken on this side? The HBr bond's broken, because I don't see an HBr bond over here. HBr bond is worth 87. That is in the table on the front. Now it may say 86, because some tables are off by like a tiny little bit. They just vary from experimental. You add these up, you get 150. 150 what? Kcal per mole. That's the bond energy of the bonds that were broken. What bonds were formed? We got a new CH bond. Because over there we got 4 CH bonds, now we got 5 CH bonds. But the new one is, they're all the same really, for this example. It's a saturated carbon, it's a primary carbon. Which one is new? I think we can say which one's new. I mean, basically one of these is new, right? Okay. That's a primary carbon because it's bonded to one carbon. So it's a primary CH. Is that in the table on the front? Primary CH in the front?
Yeah, the second one.
101 kcal per mole. That's what it says in the table, yeah? Everybody see it? Okay, so that's there. How about a CBr? Because we also made a CBr. We made this bond too. How much is that worth? See, there's bromines on different types of carbons. This is on a primary carbon. So the bromine on the primary carbon, it says 72. Okay, this actually says 79. I'm just going to write 72 there, because later on you're like, where did you get 69 from? It says 72 in the table, okay? Some other table said 69. It doesn't matter. What we're going to do is do the numbers and see. Okay, what was formed? 170. What's the difference between the two? It's 20. Is it positive? Okay, delta H is the difference here. Is it positive or negative?
Negative.
Positive or negative? Did y'all do this in Gen Chem? Negative 20 kcal per mole. Is that right? Negative 20? Why is it negative 20? Well, let me rephrase my question. Why is it that? Okay. I don't like to rely on formulas. I don't like to ask you to rely on formulas. I like to understand what's going on. Which side is more stable? Left or right? Were you reading right here? This side's more stable. Why am I saying this side's more stable? Because we broke 150 and we made 170. What does 170 mean? 170 is the strength of these bonds. The bigger the number, the stronger the bonds. This is the amount of energy it takes to break these bonds. It takes more energy to break these bonds. These bonds are more stable. So is this reaction endothermic or exothermic? Well, let me go back here. This side's more stable. Yes. Is this side higher in energy or lower in energy?
Higher energy.
Lower in energy. More stable bonds or lower in energy? Since they're lower in energy than those, where did the energy go when these were made? It was released. Energy released. Because these bonds are more stable by 20, because they're stronger. Where did the 20 go? It can't just disappear. It's released. And when we release energy, what is delta H? Negative. Okay? What does that plus mean? That's because that's what else was formed. If you do this reaction, you're going to warm something up. Delta H, it releases, this is exothermic. Yes, it is products minus reactants. No, that's not right. Yeah. See, I don't even know what it is. I don't do it that way. I look at it and say, this side's more stable, difference is 20, it should be negative 20 because this side's more stable. That's the way I do it. Everybody understand why it's negative 20, not positive 20? So there it is. It's 150 minus 170. I reckon that's reactants minus product. So what can we say about this reaction over here? It's favored. That reaction down there is favored by enthalpy. Delta H is favorable here, right? What about delta S? So that's favored. What about delta S? Not favored. Why is it not favored? Because two molecules are going to one. That's getting more order. Nature doesn't like to become more order. Okay? So one term says it's favored, one term says it's not. So you got to put it all together. Ultimately, is this a favored reaction or not? It may depend on the temperature, yeah. Do you want to heat this reaction or not?
No.
No, because heating will magnify the bad term. We will not ultimately answer delta G. Because delta G gets very complicated. We'll qualitatively assess delta S. We will quantitatively, with our calculator, do this one. The overall delta G, we're not really going to go there. That gets very detailed and tough to say. Okay, everybody got your calculator? Here's one here. Calculate delta H from the following reaction, tell them it's exothermic or endothermic. If you react 2-methylpropane with fluorine, you can get 2-fluoro-2-methylpropane plus HF. What's delta H for this reaction? Use the table on the front. What bonds are broken, what bonds are formed, add it up. As soon as you get an answer, yell it out. Is that what's broken? That's what's formed? Is that right? What's the tertiary CH worth? 99, is that right? 90? 97? What is it? What is the unit? All right, we'll write the units at the end.
Negative 116.
Negative 115? 115? What is this, kcal? Yeah. What is a tertiary CH?
I have a question. How do you know it's the tertiary carbon and not one like this?
Well, that H right there is gone. Right? That H is gone. So it's broken. How much is the tertiary CH?
97.
97?
97.
Okay, I'm assuming that's right. What's the FF? 38? That's quite low. That's one reason F2 is so reactive, because it's such a weak bond. Okay, what do these add up to? 135? Okay, this is broken. What's the form? HF?
136.
136. A tertiary CF. It may not be a tertiary CF. It may only be. If there's only one, let's use that one. 115? What's that? 152? Is that right? What's the difference? Minus 135 equals, what's that, a 6? What's that, a 1? Is that 116? Okay, is it positive or negative? This is 135. Are the products stronger or weaker? Stronger. So are the products higher in energy or lower in energy? Lower in energy. Yes. So that means they've lost. This has lost energy. So this is going to be negative, right? So we get that. Where does the energy go? I'm assuming that's kcal per mole in that table. Energy is lost to the surroundings. We can warm our hands up or something. So that reaction is classified as exothermic. Yeah? And we put a number on it.
Hey, Dr. Stevens.
Hey.
When you talk about lower in energy, do you mean like lower in like total energy or potential energy?
Yeah. Yeah. Yeah, because we start with a certain amount of energy. This is lower in energy because some of it was released. It has to be lower in energy.
Yeah.
Yeah, I mean, bonds, potential energy.
Right.
Yeah.
Okay.
Exothermic. There you go. What type of reaction is this? There's only like 5 types or 6 types of reactions. We saw an addition, elimination. What is this? This is substitution. A substitution reaction. We're substituting the H for an F. Okay. Is this reaction favored or disfavored? It's favored by enthalpy. What about entropy?
Favored.
It's sort of a wash. 2 molecules going to 2 molecules. We'd have to really look at some other things to really assess entropy. Entropy is very tough to me right here. Okay. Enthalpy, though, we did it. Okay, I think it asked you to, at the bottom, to repeat this with iodine instead of F2. See your answer and then say why the big difference in the 2 reactions. You can kind of do that on your own. But I want to take you back to the first page. 2 reactions up there. Those are decomposition reactions. 1 molecule turning into 2 things. Maybe called elimination reaction. Which reaction above gives off the most heat energy? How would you determine that? You do calculations for both, just like we did. Okay? Which reaction is endothermic? Well, you would look at your 2 answers and you would see which one's endothermic. Sounds like one may be endothermic and one may be not. Which reaction occurs fastest? Ah, that's a totally different thing. Because now we're not talking about thermodynamics, we're talking about kinetics. We can skip to 4. Are the reactions above driven by entropy or not?
Yes. First one.
1 molecule going to 2, or you can say 2 molecules going to 4. Is that driven by entropy? Yeah. 2 going to 4, yeah. So hopefully we can answer 3 of the questions now. Can we answer the 4th one, but number 3? Which reaction will occur fastest? Well, let's see if we can figure out how to answer that one. All right, what I want you to do is, we're going to move ahead, but for next Tuesday, I want you to be ready to have your answer for all those. Okay? So let's look at kinetics. So kinetics describes the rate of a reaction, the speed of a reaction. It has nothing to do with heat released, heat gained. Although maybe we could use that to assess rates a little bit. Mainly depends on the activation energy required for a reaction. Activation energy.
Hey, Dr. Stevens, real quick. Since we don't really have values for the entropy of that previous example, we really can't say for sure.
Right. Can't say. I don't know. It's 2 molecules going to 2, right? Which one are you talking about?
Yeah, that one. That's
Yeah, it's hard to assess. I mean, you could, if you get into assessing more of it, conformations or rotations or solvation or something, but I'm not going to get into that here. I just did very simply 1 going to 2, and I also showed the example of when you make a ring, you lose flexibility. Okay, kinetics. Of course, the example is, diamond will react with oxygen very exothermically. Does that mean that it's going to react with oxygen? No. If so, people would wear diamonds. Girls would wear diamonds on their finger. Blow up in oxygen. Why doesn't it happen? It's very exothermic.
Slow.
Because it's too much activation energy. Okay? It's favored thermodynamically, but it's not favored kinetically. Okay, we'll be looking at reaction coordinate diagrams, where we kind of plot the energy. We'll just kind of see examples of these. They look like this. We start with reactants and we go to products. On this axis here, we have progress of the reaction. Basically, you start and you go and you finish. Okay, the reaction. Here, some type of energy. It can be delta G, it can be delta H. It can vary. Basically, this is energy. You can go up for higher energy. Here, reactants here, some arbitrary. It doesn't matter what the absolute value is. The important thing is products are lower. Okay, so this reaction, we're plotting delta G here. This is delta G. It could be delta H. But they're saying that delta G is negative. Okay, the energy of the system is dropped. The system has lost energy, and so it's negative delta G. So this is thermodynamics here. But here we show the activation energy, because to go from this energy level to this energy level, we don't do that. We usually have to go over some activation barrier or energy barrier. It's called the activation energy. And if you don't have enough energy to get over that, it doesn't matter how exothermic it is. It can't fall downhill and release the heat. Now, if we compare this one over here, this one looks like, so that looks exothermic. Or if you talk about delta G, you have the term exergonic. Okay. This one is endergonic because the products have gained energy. You see how we say it's gained compared to these? And so that's a positive delta G. All right. So that's just pretty introductory there. KEQ, that stuff is in Gen Chem. We're not going to do much with equilibrium constants. We look at these 4 down here. Of these 4, we can ask a question. Which reaction is most favorable? Well, A looks exothermic or exergonic. That's endergonic. That's endergonic. Hold on. Okay, the top two are exothermic, right? Exergonic. And these two are endo? Okay. What was the question asking? What does most favorable mean? Yeah, you need some clarification on that. Which reaction is most favorable? Well, I'd probably look at the top two because they're exothermic. Favorable. Well, of the top two, which one do you like occurring? A. Why A?
Lower activation.
Yeah. The other thing is that the same as this?
No.
This is more exothermic, right? Or exergonic. I think that's more favorable. See, the question's vague. What does favorable mean to you? Sort of like spontaneous. Did y'all ever clarify this in Gen Chem? Basically, it's kind of a vague term, which is more favorable. I'd rather say which is more favorable based on delta H. If I said that, what is it, A or B? B, because it seems to be more negative, more exothermic. Now, which favorable reaction? Sounds like more than one's favorable. Okay. I think both of these are favorable. Which of the top two is fastest?
A.
A. Why is A fastest?
Lower activation.
Lower activation. All right, now we're going somewhere. A should be the faster reaction, but it doesn't look to be the most exothermic or the exergonic. Basically, again, rate does not equal exothermic. Okay, let's look at this down here. There's a couple of questions. Now, all the ones above, that was just one reaction. Okay. Let's go back up here again. They're all these up here. But what do you have right here? That's starting materials, reactants, products. What do you have right here?
Activation energy.
Well, that's the activation energy. But what exists right here? Somebody said something. Activated complex, yeah. It's where bonds are partially breaking, partially forming. The activated complex. Not an intermediate. Somebody said intermediate. An intermediate is a discrete thing where all bonds are formed. Below, we're going to see an intermediate. That's an activated complex. All right? Y'all got your Gen Chem book? I know nobody sold that thing back, right? Go look up activated complex, okay? That's what it is up right there. Okay, now look down here. Here we're going to have an intermediate. These two react to give this, but there's an intermediate. Intermediate's going to have a well, okay? Because it's a discrete species. We have an activation complex, an activated complex leading to that. Activation energy leading to this intermediate. Then we have another activation energy leading to the final product. And so it ends up being your intermediate sit in this sort of well. Okay? So you got to recognize that there's one intermediate there. This can also be called activation complex or transition state. Activated complex or transition state. There's a transition state leading to the intermediate and a transition state leading to the product. This being an overall exothermic reaction. Question is, there's two steps here. Formation of the intermediate, formation of product. Two steps. We can ask a question here. Of the two steps, which one is the rate determining step?
F. This is your rate determining step. Okay, I can't draw it all up there unless I lower it down. So we got a pretty big activation energy. Now this step over here, the activation energy from the intermediate level to here is not as big. Bigger activation energy is going to be your rate determining step. What do you want to call this step? Fast step, good. All right. That's your fast step. Rate determining step is sometimes called the slow step. If all you were going to exit this room and it took 2 steps, standing up and then walking out the door, which would be the rate determining step? Walking out the door, you got a bottleneck. Everybody's going to stand up fast. Okay? So if I wanted to get you out of this room faster, do I need to worry about getting you through the door faster, or do I need to worry about having you stand up faster? Yeah, getting through the door. Having you stand up 100 times faster ain't going to help us do anything. If you want to improve the reaction rate, you got to focus on which step? Slow step. The bottleneck step, the rate determining step. Okay. We got some on the back. Let's finish this up. I was wondering where these were. I thought that was the last one. Yeah. Here's 2 first steps, okay, leading to an intermediate. 2 different intermediates here. All right. This comes from the same starting material, same SM. SM is, I say, starting material. Starting material for this reaction looks like it's going to be this alkene, okay? So that's what we have right here, that alkene, that's starting material. What this is illustrating is 2 different pathways. It can form intermediate A or B, okay? A or B. First off, which intermediate is higher in energy, A or B? Well, you can tell from here, indeed this is A and this is B. A is higher energy, B is lower energy. We'll explain why. You should have a good prediction of that already. These are carbocation intermediates. We're going to be looking at this once we start reactions. All right, B is lower in energy, plotted here. This is going to be very important over here. This is the transition state energy. What we're going to usually say is the transition state energy leading to a lower energy intermediate is usually lower itself. B is lower in energy, and so the transition state leading to it is lower in energy. Now that's sort of an assumption, but that's what we're going to always usually say. So, which pathway is going to be preferred? Forming A or forming B? Forming B is going to be favored. Not because it's lower here. That's not the reason. The reason is because it's lower here. It's easier, that's a lower mountain to go over. Okay? So when this reacts, it's going to prefer to form B. That's going to be the preferred intermediate, and we're going to get a preferred product from that. We're going to be able to have to do things like that to assess our reaction coordinate diagrams like this. Now that's not always the case. That assumption is not always the case. Down here we have an exception to the assumption. In this, which we look at during test 3, this exact reaction, we get two products, a 1,2 product and a 1,4. The 1,4 is lower in energy. Now it's lower than the 1,2. Now, our assumption is because that's lower energy, the transition state leading to it should be lower. But is that correct in this case? No, it's not. Our assumption fails. So while we will use that assumption, sometimes it will fail. So in this case, if we're right here, which is going to be preferred?
1,2.
Well, this pathway is preferred, right? And that gives us which one? 1,2 product. That is, if we just base it on, if it's non-reversible. Okay? We won't get into any more of that. That's an exception to what we said above. Okay, what's at the bottom here? Bottom is just another one. I think we've already seen this. Why is it here? Looks like just one reaction. How many intermediates in this reaction coordinate diagram? 0. I don't see an energy well. Just one reaction. This is just what? An activation energy. There's a transition state there or an activated complex. I usually call it transition state. Type of transition state, and we get here, no intermediate. That's an SN2, by the way. We'll do SN2 during test 3. Okay, I think we covered everything. Please do the ones on the front. Questions about that page, that handout? Again, I apologize if you didn't get a purple handout today. I'll put some on my door. Somehow there'll be a, like this. Please come by and pick one up tomorrow, okay? Because on the purple there are some warm-up questions. This is what I'll also do. I may send this by email, okay? We're going to look at this. We're not going to do any work here. I'm just going to kind of just show you some things. Basically, the first two reactions there, I call them warm-ups, but there's nothing really sophisticated about them. Those are basic reactions. Okay, usually my warm-ups, I give you something that's sort of interesting, a little bit fancy application. That is just straightforward. Okay, we've got to be able to predict products of those reactions like that. There, that's a little application. Okay. Electrophiles and nucleophiles, terminology that we'll use. Say electrophilic, we'll also say electrophile. What is an electrophile? What is an electrophile like? It likes electrons. What type of charge? Yeah, if it likes electrons, it apparently likes negative charges. Because electrons are negative charge. So we take from that name that it's something that likes a negative charge. So if it likes a negative charge, what do you think its charge might tend to be? Positive. Positive, because positive like negatives. Electrophiles tend to be positive. So does the terminology make sense?
Yes.
Thanks. Now it can be a full positive like a cation, or it can be a partial positive. I mean, do we have a partial positive anywhere here?
Yes.
How about right there? Is that partial positive?
Yes.
Yeah. So we say that carbon has some electrophilic character. Because it's partial positive, positives like negatives, and if you like a negative, we call your electrophile. Question?
So is this different from electronegativity? Because I would think that like chlorine likes electrons because it's attract the electrons to itself?
Yeah, but chlorine is not called an electrophile. Because chlorine has a lot of partial minus. Because it pulled the electrons towards it. Okay? Now, if some electrons are floating by, what's the charge of electrons? Negative. So let's put negative there. Which one of these are going to be attracted to this guy? That one. So we say it's the electrophile. It's the one that likes the electron. Good question. Everybody see that? This is the one that likes the electron. Electronegativity, yeah, chlorine likes electrons, but it's done. It's got the electron. Which one likes the electrons? Or the minus? That's the main thing. Positive likes minus. Don't forget about that. Positive like minuses. All right? It's a really simple thing, right? But you got to keep it simple. I try to keep it simple. We'll look for positives. We'll look for minuses. Those are going to react. Okay? So there's terminology. Okay? What would I recommend? I recommend turning to your index and looking up electrophile and nucleophile. All right? Online, electrophile and nucleophile. Mechanisms. Down below is sort of a sophisticated looking mechanism. In actuality, it's not really. It's pretty straightforward. We will do mechanism. I showed you an acid-base mechanism. There was one handout in the acid-base packet. Okay? Using curly arrows. Mechanism arrows show movement of what? Electrons. Okay? It does not show movement of atoms. Every time I use a mechanism arrow, I will begin by saying what? No, that's what I'll ask you after you don't get it right. I will start by saying these electrons. These electrons. These electrons will do something. I will never say this atom will do something. These electrons. I'm recommending you look in the textbook, you look in the wiki or wherever, and you look up. If you look on Wikipedia, or you look under arrow pushing, you will see a little bit of stuff about using arrows to push electrons. All right? Here's a basic example. In this example here, I've got a molecule, I've got a reactant, and lots of products. There's 4 of them. Okay? Show a mechanism for all that. How does this take place? What does the mechanism show? Mechanism shows forming and breaking of all the bonds. What makes bonds? Electrons. You got to show the electrons making the bonds. You got to show the electrons being broken apart to break things apart. I'd recommend Lewis structures of those things over there, because we always need to show complete Lewis structures. Assess this. What's bonding to what? Let me make it a little bit smaller. You got to assess what's going on here. Somehow that's breaking apart into 4 things. We got cesium fluoride. By the way, this is organic chemistry. Group 1, Group 2, forget about it. This is F minus. Okay? What do we call Group 1, Group 2? They sit on the sidelines. They are spectator, bench warmers. They don't do anything. That's fluoride, F minus. Okay? It's a catalyst. What's the definition of a catalyst?
Lowers activation energy.
It lowers activation energy, but the main thing for me is it's not consumed. It's reproduced at the end. It's still there at the end. What's going on here? Anytime we do a mechanism, okay, what bonds do we need to make? If I look over here, I've got a fluorine bonded to a silicon. There's no fluorine bonded to a silicon here. What do I need to do? Bond fluorine to silicon. If you look at the directions, it says the first step is bond fluorine to silicon. How do we make bonds? Okay? Now, when we make bonds, it's going to be overly simplistic. You're going to say, is that it? But at the same time, you're going to tend to get it wrong. Fluorine is bonded to silicon. So I'm going to say these electrons are going to bond to silicon. That's what that arrow means. Okay? Well, silicon's below carbon. It can only make 4 bonds. The silicon's no longer bonded to oxygen over there, is it? So what does the oxygen have to do? It has to debond from silicon. I've never said debond before in my life. But it has to leave silicon. And when an atom leaves, what do we call it? We call it a leaving group. That's pretty simple, right? Oxygen has to serve as a leaving group. But what about the 2 electrons there? What happens to those? Well, we need to know what a full Lewis structure here. Do we need those electrons here in this structure? When you do your structure, no, you don't need them. They go with the oxygen. So you want to show them breaking from the silicon going. Okay? I think that's all I'm going to do. Sorry again, you don't have this. But I've given you just a little bit of, okay, what are we doing with the mechanism? Please try to work all that. What bonds do you need to make? What bonds do you need to break? We show arrows of all electron movement. Okay. Forget. Let's move to the handout. Everybody got the addition of HX? I tell you, I really don't want to start that handout today. Instead, let's do this. I want to finish up, because what I want you to do is I want everybody to get that warm-up page, read mechanisms. Okay. Let's finish up the intro page. Okay. The first 2 pages are on the video. How many have watched the video? Good. I'm not going to ask for questions right now, but let's look at the second page. Let's do this because with 15 minutes left, we don't want to open up the big can of worms on the other set. The big can of worms will be opened up on Tuesday, okay? I'd recommend doing some reading. I think it's chapter 9 or 10. There's also a chapter like 6. Everything's in the syllabus. Okay? All right, big time starts Tuesday, guys. All right, let's see what's here. By the way, in lab next week, you're also doing an alkene reaction with dehydrating norbornene, sulfuric acid. That's a synthesis reaction next week. The first synthesis. You'll do purification by sublimation. Okay, physical properties of alkenes. What types of questions can we ask here? Very similar to what we saw before. Which alkene will have the highest boiling point? Now, one thing I explained in the video is, we already should know these are different compounds. Okay? One of them is cis, one of them is trans. Cis, trans. Because of the pi bond, the chlorines are fixed like that. They can't rotate down. Fixed, cis. 2 different compounds. Which one's got the highest boiling point? This one has dipole like this and like this. This one has dipole like this and like this. Do any of those cancel? This is nonpolar. The 2 dipoles are equal and opposite. That alkene is nonpolar. This one's polar. It has a net dipole molecular moment sort of straight down. So this one's polar. Which one has the highest boiling point? Polar one. Why? Because it has the greatest amount of IMFs. Dipole-dipole interaction. Which one's most stable? Cis or trans? Just like conformations, do the big chlorines want to be sort of next to each other like this? That's sort of analogous to sin, right, in a conformation? Or do they want to be away, anti? Yeah, it's very similar to that. Trans, all right, most stable. Now these are not conformers, they're different compounds. But we can use our knowledge of conformers to help us predict that most stable, because still you got the same idea. These 2 just happen to be fixed that way. What's the one on the right say? Most soluble in water? Which one's most soluble in water? The polar one. Now, I guarantee you this is probably not that soluble in water. But I bet it's more polar than that, or more soluble than that one. Because at least it has some polarity that can interact with the polarity of the water. Out to one below. Which one of these is most stable?
But I want
Alkenes, yeah? What's the difference in these? By the way, what's the relationship between the top two? Stereoisomers. Same connectivity. One cis, one's trans. Otherwise, they're both called 1,2-dichloroethene. Same name, just one cis, one trans. What's the relationship between these two? These are constitutional isomers. They have different names. Which one's most stable? All right, this one's a little bit tougher. The take home here is, first off, these are isomers. They're both C4H8. They are isomers. With your alkene isomers like this, the more substituted alkene is the better one. When I say substituted, I'm talking about carbon substituents. This alkene has 2 carbon substituents. This alkene only has 1 carbon substituent. More substituted is going to be more stable. Why? Why can be explained below. But before we explain it, let's tell me which one of these 4 down here is most stable. These 4, they're all isomers. Which one's more stable? Tetrasubstituted. See how it's tetrasubstituted? It's got 4 groups on the alkene portion, alkene carbons. Most stable. Why? Why those? You can answer that by looking below. It has to do with the types of bonds that are there. This table explains it. Using the last 4 in the last example, let's look at the types of carbon-carbon bonds. The types of carbon-carbon bonds give you the answer. All 4 of those have one of your sp2-sp2 hybrid bonds. That's the signal bond here, 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 and here. Of course, they also have the pi bond. That's not even on the list. All the same here. Let's look at these 2 types, sp2, sp3. This one only has 1, right here. sp2, sp3. There's only one of those types. This one has 2 of those, here and here. sp2, sp3, sp2, sp3. This one has 3 of those types, and that one has 4 of those types. Okay? 4, 3, 2, 1. Now, if we look at sp3, sp3, it's just the opposite. This one has the most of those. I'll do X's, okay? It has 3 of those types, where this one over here has how many of those types? X has none. This is the key difference. Which bond is stronger? Top or bottom? That's a stronger bond. And that one has 4 of the stronger bonds, where this one only has 1 of the stronger bonds. Stronger bonds means more stable. So which one's more stable? That one. The take-home was, the more substituted, the more stable. That's why it has more of the sp3, 2 sp3 carbon-carbon bonds. All right?
What if like a constituent or like a
Something other than carbon is a substituent?
I mean, if there's a chain on a chain, like does that contribute to it?
You mean out here?
Yes.
No, we're really looking at that. We'll see plenty of examples of this along the way. Take home, more substituted alkene, more stable, especially when you're comparing isomers. If we start comparing very different compounds, we can get into apples and oranges. See, but these are isomers. There's some questions down there. We said which is most stable. Which of those four has the lowest heat of formation? Lowest heat of formation. What does that mean?
That is just also the most heat of the lead.
What is the heat of formation? That's the amount of heat that is released when it's made from the elements. Lowest. Now see, lowest can be misleading because if we're negative, lowest is actually a greater whole number. Because which is lower, negative 10 or negative 5? I think get negative 10 lower than negative 5. So you got to be careful. You got to know what you're. Usually HF heats of formation of exothermic. All these are going to be exothermic. Is lowest HF asking for the most stable or least stable? Least stable. Of these, which is the lowest, negative 5 or negative 10?
Negative 10.
Yeah, this one. kcal per mole. So this is the lowest. Now, HF is the heat release when it's formed from the elements. So this means that the most heat is released here. If this releases a lot of heat, what does that tell you about the stability of what was made?
Very stable.
It's very stable. Lowest HF is asking for which is most stable. See, this is the same question. And it's the same answer. Which one? Okay? What I implore you to do is please understand what you're being asked and not just say what's the formula and plug and chug and okay. All right? You really want to understand, then the stuff can make more sense. Question?
So that, the lowest being the most stable only applies when it's exothermic, correct?
No, because it always applies. Because what if you got plus 20 and plus 10? Which would be more stable? Plus 10 would be more stable. It still would apply. Right? Which gives off the most heat when burned? Why is that important? Because factories produce heat by burning something. Which gives off the most heat when burned? Are we looking for the most stable or least stable? Yeah. Which gives off the most heat when burned? The one that contains the most heat and energy. Which one is that? The most stable or least stable? Least stable is going to contain the most heat energy. So if you wanted to buy these and you were going to buy a kilogram and burn it, which one would you rather burn? The one that contains the most energy, potential energy in it, right? Yeah, this one's got the most potential energy. It's got the highest energy bonds. Or the least stable bond. Because least stable means they're higher in energy. So that's some of the types of questions we'd ask. Let's finish up by looking at a couple of miscellaneous pages. Everybody heard of fatty acids, trans fatty acids? Let's look at this. On the top, that's called a saturated fat. Fatty acid. See, they're all carboxylic acids. You see the side chain, which is like 12, 14, 18 carbons long, it's all saturated. You don't see any saturation in it, do you? No pi bonds? Okay. Saturated fat. Melting point is 69. It's a solid at room temperature. It's a solid in your veins when you get a lot in there. Clog up your veins. If we can put one double bond in there, now it's monounsaturated. What does that do to the melting point? It really lowers it. Now this is a liquid at room temperature, like olive oil, not like Crisco. Olive oil, liquid at room temperature. Why does this make it a liquid when we put in one double bond? Now that's also a cis double bond. It puts a kink in it. Okay? See, if they're all straight, they can just stack up, one on top of each other. I can stack 10 of these on top. All right? But if you got a big kink in it or something, you can't stack them as well. They're not going to come together and stack. And so the kink decreases the IMFs. I'm sorry, yeah, monounsaturated. Now we got more than one. We call this a polyunsaturated fat. I mean, any of these with your cis alkenes are going to be sort of low liquids. These are your better fats. Once you saturate them, they become solid. But there's also another problem. Fats that have trans double bonds, so your trans doesn't lead to the kink. Now there is a kink here. That's why it's lower than the totally saturated. But when you put trans double bonds, it sort of straightens it back out compared to these, and your trans ones start going back up. So your saturated fats and your trans fats are your worst ones because they're solids at room temperature and they clog up your arteries. The other ones stay more liquidy. I think the last couple of pages you can sort of read on your own. There's just a couple of more miscellaneous applications of your alkenes. So Tuesday we'll start alkene reactions. Okay. Please watch the video of the nomenclature if you haven't done that. Hydration of norbornene in lab next week. Anything else? Okay, guys, have a good weekend. See some of you tomorrow, I know. Body lab.